All right, let's talk about something pretty wild. We're going to dive into a corner of quantum physics that has some truly massive cosmic consequences. It's called Compton scattering.
So, let's start with a cosmic mystery. When our telescopes look out into space, they see these incredible, powerful flashes of light, things like X-rays and gamma rays. The question is, what out there is powerful enough to create them? Well, the answer is kind of weird, and it all comes down to a strange dance between light and matter.
To really get our heads around where these powerful flashes come from, we have to start with the basics. The simple, classical way that light just scatters.
This is what we call Compton scattering. Just imagine a little light wave coming along and gently nudging an electron. The electron starts to wiggle, and it sends out a new light wave. But the key word here is elastic. Think of it like a perfectly bouncy ball hitting a wall and bouncing off with all its energy.
So what that means is, the light that comes out has the exact same energy and the exact same color as the light that went in. The photon doesn't lose any of its juice. And for a long time, we thought that was the whole story. Until quantum mechanics blew everything up.
Okay, and this is where it gets really, really cool. Because quantum physics came along and told us that light isn't just a wave. Nope. It can also act like a tiny little particle.
That's right, a photon, a single particle of light, actually has momentum. It can pack a punch. And this changes everything about how we think of a collision. It's not a gentle nudge anymore, it's a real physical impact. Now this slide here shows the physics, but don't worry about the equations. The real story is right there in that little diagram. Think of it like a game of cosmic billiards. The photon comes in like a cue ball, smacks right into the electron, and they both go flying off in new directions.
And this is Compton scattering. Now, unlike that gentle Thomson scattering, this collision is inelastic. The photon slams into the electron and actually gives some of its energy away, literally knocking the electron for a loop. And since the photon lost energy, its wavelength gets a little bit longer, which means the light gets a little bit redder.
So let's just put it side by side. It really is this simple. Thomson scattering is like a perfect bounce, no energy lost. Compton scattering is a real collision, where the photon gives up some of its power to the electron.
And here's the really wild part. How much energy the photon loses depends only on the angle it bounces off at. It has nothing to do with how much energy it started with. So a head-on collision that sends the photon flying straight back transfers way more energy than just a little glancing blow.
So far, we've just talked about a photon losing energy. But out in the most extreme places in space, this whole process can get flipped completely on its head, creating something spectacular.
What happens when the electron isn't just sitting still waiting to get hit? I mean, what if the electron is the one that's supercharged, blazing through space at almost the speed of light?
This, my friends, is inverse Compton scattering. And here, the roles are totally reversed. You have a super fast, high-energy electron that smashes into a lazy, low-energy photon and gives that photon a colossal boost of energy. The electron is the powerhouse, and the photon gets shot into the big leagues.
Okay, think of it this way. A low-energy photon is like a tennis ball just sitting on the ground. The relativistic electron, that's a freight train barreling down the tracks at 99.9% the speed of light. When that train hits the tennis ball, it doesn't just nudge it, it launches it into orbit. That is how you turn faint starlight into a powerful X-ray.
In this graph, it might look a little complicated, but it shows us exactly what's going on. See that little bump on the left? That's the photon's original low energy. But after the collision, look how the peak of its energy gets shifted way over to the right. That's a huge gain in energy. This is a cosmic particle accelerator in action.
Now this isn't just some cool physics trick. This cosmic slingshot is actually one of the most important tools we have for understanding the most violent, energetic, and frankly awesome places in the entire universe.
So why does all this matter? Well, because these super boosted photons, they act like messengers. They travel across the cosmos to our telescopes and tell us about things that we could never ever see directly.
You know those incredible jets of plasma that we see shooting out of supermassive black holes? Or the enormous clouds of superheated gas that are trapped between galaxies? Or the glowing leftovers of stars that have exploded? The only reason we know about the crazy physics going on there is because we can see the X-rays and gamma rays that are created by inverse Compton scattering.
And the energy boost we're talking about is just staggering. It can be up to 1 billion times the photon's original energy. It's just an incredible amplification, and it happens because the boost is related to the electron's energy squared. That's what makes this cosmic slingshot so unbelievably effective.
And here it is. This is the big takeaway. Those super fast electrons, the ones doing all the work, they're totally invisible to us. We can't see them. But when they collide with photons and create this high-energy light, that light travels across the universe and hits our detectors. It's like a message in a bottle that says, hey, there is something unbelievably powerful happening back here. So the next time you hear about astronomers spotting gamma rays from some faraway galaxy, you'll know the story behind that light. It's a story of a cosmic collision, of a powerful slingshot that lights up the universe's biggest secrets. And it just leaves you wondering, what other secrets are still out there, hidden in that scattered light?